Hello, everyone, and welcome back to Math 127 Pre-Calculus 2. So, this is the second part of section 4.7. I hope you had the opportunity to watch part 1, where we introduced the concept of inverse trigonometric functions and then discuss the foundational ideas behind them. All right, for the second part of the lesson, we will apply and connect the concept we learned throughout chapter 4, including the six trigonometric function, their graphs, the fundamental identities, and especially the special right triangles. So you will see how these ideas work together as we use the inverse trigonometric functions to solve problems and analyze trigonometric relationships. Okay, so let's go ahead and start. All right, so now let's go ahead and find the exact value of the two following expression. So the first one, let's say we have here the sign or the inverse sign of radical 3 over 2. So you notice here on this side, I have written all the concepts that we went over from the past sections of chapter 4, and we will all be applying all this concept that you see here in order for us to evaluate or find the exact value of this expression. Okay, so now since I have mentioned that whenever you are dealing with the inverse function, the very first question that you need to ask yourself is what angle has a sine, for example, in this case, has a sine value of square root of 3 over 2. Okay, so that means to say we are looking for that angle. So let's say the angle is theta. So I'm going to right, angle theta is equal to inverse sine of radical 3 over 2. Okay, now I'm going to rewrite this statement in a way that I do have this form of equation. Okay, so instead of having that inverse function, I am going to write the sine in front of the angle. So in this case, I can also write this as sine angle theta is equal to radical 3 over 2. And as you can see here, on top of here would be the definition of a sine function in terms of a right triangle, that it says that the ratio between those two numbers is the numerator is the opposite side, and then the denominator is the hypotenuse side of a right triangle. If that's the case, then we can say that this radical 3 over 2, that this radical 3 would represent an opposite side of a right triangle, and then this denominator 2 would represent the hypotenuse of a right triangle. Okay, so recall that we went over with the special right triangle, wherein we do have the 30 by 60 by 90 degree triangle and 45 by 45 by 90 degree triangle. And then also I have assumed that the hypotenuse here is 2, and then we have found those sides of a right triangle. Now, what we are going to do is to locate those values, radical 3 and then 2, from any of these two triangles. And as you can see, the applicable triangle that we have here is the 30 by 60. Okay, so let me just go ahead and encircle those values that are given in the statement, which is the radical 3 and then the positive 2. Okay, so we said that radical 3 should represent the opposite part of a special right triangle. So as you can see, this radical triangle opposite to that would be the angle radical, sorry, not radical, but pi over 3. Okay, so we can now say that this is pi over 3. So if I'm going to write this, let's see if this um, works. So we have here the sine pi over 3. We said that radical 3 over 2. Okay, let's go ahead and check if this statement is correct. So as you can see, if I am going to evaluate sine pi over 3, that would be opposite over hypotenuse. And it is correct. It's radical 3 over 2. Okay, now we can now say that angle theta is equal to pi over 3. Or we can say that sine or inverse sine of radical 3 over 2 is equal to pi over 3. Okay. All right. Now, how do we know that this is also, again, uh, not how do you know, but you have to make sure that this computed angle here is in quadrant 1 or quadrant 4. Okay. But not only that, and we can see that quadrant pi over 3 is in quadrant 1. But aside from looking at if the angle is within these two quadrants, not only that, but the angle measurement itself should be within the principal interval. What is the principal interval for the sine? It is from negative pi over 2 to pi over 2. And pi over 3 is within this interval. As we can see that. Okay, so therefore, we can now finalize our answer that indeed that inverse sine of radical 3 over 2 is pi over 3. All right. Okay, now let's go ahead and try once again with the next statement, which is the inverse sine of negative radical 2 over 2. So again, let me go ahead and write this as a statement of with an angle theta, let's say. So inverse sine of negative radical 2 over 2. So I can also rewrite this as sine theta, which is equal to negative radical 2 over 2. Now you notice that I gave that negative sign to the radical 2 because I know that this denominator here represent the hypotenuse. Okay, and then that numerator here represent the side of the opposite side of the right triangle. Okay, so in this case, I am going to now locate which of these two triangles is applicable for this particular problem. And then now I see on the second triangle here, there's a radical 2, and then of course our hypotenuse, which is 2. Okay, so let me just circle that. So those two values. And then you have to remember that this opposite side right here is again under the definition of sine. So that's what we are going to apply. So opposite of radical 2, okay, which is the pi over 4. So let's go ahead and write that. So now we say that sine theta is pi over 4 is equal to radical 2 over 2. Can we say that pi over 4 is equal to radical 2 over 2? Yeah, that's correct because if you're going to evaluate pi over 4, okay, opposite over hypotenuse. As you can see here, opposite is radical 2 and then hypotenuse is 2. Now, if you notice as well, I have written here that the radical 2 over 2 is positive. But the original given here is negative, and that should be the case. So this should be a negative sign. Now, what does it mean? If you have a negative sign of, if you have an output which is a negative under the sine function, we know that that would be either in quadrant 3 or quadrant 4. And obviously, our principal interval should only be in quadrant 1 or quadrant 4. And so, if that's the case, therefore, we are assuming that, if that's the case, that again, negative sign for the sine function, it's either quadrant 3 and quadrant 4. And the principal interval, it says here, should only be from quadrant 1 and quadrant 4. Now, you notice the overlapping quadrant that I have mentioned would be quadrant 4. So, therefore, the terminal side is located in quadrant 4. Now, how are we going to write our angle now? So definitely pi over 4 is not in quadrant 4. Okay, so we know that in quadrant 4, if you are going to apply the terminal side wherein the rotation is clockwise or counterclockwise to be in quadrant 4, that would be beyond the principal interval. Okay, So the technique here now is that you just need to rotate that terminal side by clockwise. If that's the case, that would be a negative pi over 4. So that that terminal side will be in quadrant 4. Okay, so what does it mean? That this angle pi over 4 needs to be a negative sign. Okay, and you can check, is negative pi over 4 within the principal interval? The answer is yes, because negative pi over 4 is within the negative pi over 2 and then pi over positive pi over 4. And then also we can also check that in the coordinate plane, because if you're going to rotate that angle clockwise, okay, which is a negative pi over 4, still located in quadrant 4. Okay, all right. So now let's go ahead and now we have seen how inverse sine works now. So now let's move on to the inverse cosine. So overall process will be very similar, but then again, the restricted interval will be different. Okay, so understanding why that interval changes is just as important as finding the answer itself. Okay, so just remember here for the sine function, the principal interval, and how you visualize that is make sure that that terminal side is only located in quadrant 1 or quadrant 4. And of course, when you evaluate those function, you just need to stick on the special right triangle. Okay, moving on to the cosine. Okay, so moving on to the inverse of cosine function. So like I mentioned, if you have watched the part 1 of 4.7, you will see you will be introduced with the concept of the inverse function. Okay, so it's very similar. Just like the sine function, cosine definitely is not a one-to-one over the entire domain because the values repeat itself. If you can recall the horizontal line test, if we're going to draw a horizontal line here, it will intersect the graph more than once. So just the same thing as the like I've said, same thing as the sine. We want, if we want to have a cosine to have an inverse, we must restrict its domain. Okay, so for the inverse cosine, the restricted interval here would be from 0 to pi. Okay, so we're going to restrict the domain from 0 to pi. All right. Okay, so now this interval, remember, is chosen because cosine passes through the horizontal line test now and produces every value between negative 1 to positive 1, exactly once. All right, so just like inverse sine, inverse cosine answers a question. So instead of asking for a trigonometric value, we ask what angle has a cosine value equal to a given number. Again, the answer will always be an angle. So one of the most important things to remember about inverse cosine is its range. So every answer produced by inverse cosine must be between 0 to pi. That would be the principal intervals, okay? So if your answer falls outside that interval, it cannot be correct, okay? All right, now let's take a look at the graph. So just as before, the graph of the inverse cosine, okay, is obtained by reflecting the restricted cosine graph across the line y is equal to x. All right, and then also notice that the domain and the range. Um, only switches their places. Okay, so the domain of inverse cosine is from the -1 to +1, and then the range of inverse cosine is from 0 to pi. Okay, which switches from this original function. All right. So since inverse cosine always returns an angle in this interval, so it eliminates the possibility of multiple answers. So this allows inverse cosine to truly behave as a function. Okay. All right. So now let's go ahead and evaluate the following. So remember, I am going to apply similar step like I did from the previous example. All right, so notice that I have written all the information we need in order for us to evaluate the following expression. Okay, starting with the inverse cosine of -1/2. So in this case, let me go ahead and write this with an angle since that's what we are solving. So angle, let's say angle theta once again. So inverse cosine of -1/2. Okay, let me rewrite this as cosine theta is equal to -1/2. So we can literally see the definition of the cosine. So as you can see here, I have defined the cosine theta, which is adjacent over the hypotenuse. Okay, so we can now say that the numerator here may represent the adjacent side of the right triangle, and then the denominator may represent the hypotenuse side of a right triangle. Okay, so remember the cosine here is negative. So therefore, this is in quadrant 2. And remember that the principal interval of a cosine is from 0 to pi, and that is in quadrant 1 and quadrant 2. So here is the quadrant that we are looking that we are solving for, which is for letter A. Okay, so we're in the output is a negative sign. And we know that the x value here in quadrant 2, which represent the cosine, is negative as well. Okay, so now moving on to, I do have here the special right triangle that gives us those standard measurement. So we have here the -1/2. So we see a 1, oops, so we see a 1 here and then a 2. Okay. And then remember the definition, by definition, cosine, it says that it is adjacent over hypotenuse. So I'm going to look for an angle that is adjacent with the side that measures 1. And then we see an angle that is adjacent to that side which measures 1 is pi/3. And of course, this would be our hypotenuse. Okay, so if I'm going to rewrite that now with that angle, so we say that cosine pi/3 is equal to -1/2. Okay, so now in this case here, we do have here cosine pi/3 is equal to -1/2. Okay, so is it correct that pi/3 is equal to, well, I am not gonna go write the sign first, okay? So we have here 1/2. Yeah, it is correct. So cosine pi/3 is equal to 1/2. Now, if you can recall, when we were evaluating trigonometric function, we are also using the reference angle, right? So if I am going to draw an angle here, oops, okay. So if I'm going to draw an angle in quadrant 2 that has a reference angle of pi/3, which is here, okay, pi/3. Remember, I have mentioned that the terminal side definitely that we are solving is in quadrant 2. Okay, but of course, this is not what we want. We want to have a value that is a -1/2. Okay, a -1/2. So, in this case, instead of having its reference angle pi/3, now what we are going to do is we need to have that value, okay, that value that is a standard position. Okay, that angle that is in standard position, that's what we are looking for. Okay, so in this case, what we're going to do is to apply the solving backwards of the reference angle. So we know that the whole measurement here is pi. So all we need to do is to subtract pi over 3 from the entire angle here, which is pi. So that would be pi minus pi over 3, which is equal to 1 minus 1 pi over 3 is 2 pi over 3. Okay, so in this case, therefore, our angle now would be 2 pi over 3. Okay, so to make it this value as a negative 1 half. Okay, so now I can say that cosine 2 pi over 3 is equal to 1 half, negative 1 half. Or I can now say that angle theta is equal to 2 pi over 3. Or I can say that cosine inverse cosine of negative 1 half is equal to 2 pi over 3. Okay, so there you go. And we know, let's check, is 2 pi over 3 2 pi over 3 is within the principal interval? We say it is yes. Okay? All right. So that would be our letter A. So next one, letter B, the inverse of cosine, which is the radical 2 over 2. So first, let me go ahead and write this as a angle theta is equal to inverse cosine of radical 2 over 2. And so in that case, I can also rewrite this in a statement of cosine theta is equal to radical 2 over 2. Okay, so once again, remember that cosine is adjacent over hypotenuse, and then we see a radical 2 and then 2 under the special right triangle, which has the pi over 4 angle. So we now see here that we have here that radical 2 and then over 2. And then adjacent to the radical 2 is the pi over 4. Okay, so in that case, we can now say that cosine angle theta is equal to, that cosine pi over 4, since that is the angle, once again, adjacent with radical 2. Okay, so this is radical 2 over 2. Okay, so now let's go ahead and check if pi over 4 is within the principal interval. Okay, is pi over 4 is within the principal interval? We say yes. And then where is radical 2 over 2 located? We know that a positive cosine is in, it's either quadrant 1 or quadrant 4. And obviously here, quadrant 4 is not included in our principal interval. So we are only focusing on quadrant 1. So if that's the case, and we do have here the pi over 4. Pi over 4 is also in quadrant 1. And if that's the case, then we can now say that the angle theta, that angle theta is equal to pi over 4. Or we say that the inverse cosine of radical 2 over 2 is equal to pi over 4. Okay, so there you go. That would now be our evaluated value for the exact value for these two expression. Once again, don't forget to apply the definition of cosine. And then you have to check your final answer if your final answer is within this interval. But not only that, you also have to check if that given value, if that terminal site from that given value is in the correct quadrant, okay, by looking at their sign. Okay, so that's it for the cosine function. So far, we've worked with the inverse of sine and inverse cosine. In both cases, the domain of the original function had to be restricted so that the inverse could exist. So next would be, we are going to look at the inverse tangent. So in many applications, especially when solving triangles later in chapter 6, inverse tangent becomes one of the most important useful inverse trigonometric functions. So let's see how it works and how its graph differs from inverse sine and inverse cosine. Okay, so moving on, once again, the inverse tangent function. So of the three inverse functions we've studied so far, inverse tangent is often the one of students use most frequently in later math courses. In fact, when we get to chapter 6 and begin solving triangles using trigonometry, you'll often use the inverse tangent to determine unknown angles. And then we also have seen that from our previous real world problems from the past sections. So recall that the tangent function is defined as tangent equals sine divided by cosine, right? Again, that tangent theta is equal to sine theta over cosine theta. So like sine and cosine, the tangent function repeats. Okay, so as you can see here, all right, so because of that repeating behavior, it is not one-to-one over the entire domain. So to create an inverse, once again, we restrict the domain of tangent. So the restricted interval is from the negative pi over 2 to positive pi over 2. Okay, not obviously not including the endpoints, unlike with the sine and cosine, because as you can see here, we do have those vertical asymptote. Okay, all right, so within this interval, the tangent function now passes the horizontal line test and becomes one-to-one. This allows us to define the inverse tangent function. Okay, so again, when we write the inverse tangent of x, or theta, sorry, of x, we are asking what angle has a tangent value equal to x. So once again, the inverse tangent returns an angle, not a ratio. Okay, so we have here, so you have to remember that we have here the interval negative pi over 2 to pi over 2. Now you notice that I am writing it interval notation with a parenthesis, meaning to say that the negative pi over 2 and pi over 2 are not included, okay, in our principal interval. Okay, so let's just go ahead and examine before we start with the example. So just as before, the graph is obtained by reflecting the restricted tangent graph across the y is equal to x. If you're going to draw these two graphs here in one coordinate plane, you will see that they are symmetry across with y is equal to x. Okay, so again, so one thing you'll notice immediately is that the inverse tangent looks different from inverse sine and definitely an inverse cosine. So the graph continues infinitely, as you can see, to the left and to the right. Okay, so this means that the domain of inverse tangent is all real numbers. However, the range is restricted. So every answer produced by inverse tangent must lie between, again, the negative pi over 2 and pi over 2. Another important feature of the graph is the presence of the horizontal asymptote. Okay, so as x becomes larger, okay, it approaches to pi over 2 only. So same thing as the x becomes very negative, the graph approaches negative pi over 2 only. So however, the graph never actually reaches those values, like I've said. So this is why the endpoints are not included in the range. Okay. Okay, so let's go ahead and find the exact value of the inverse tangent, just the way we did with the inverse sine and inverse cosine. Okay, all right, so let's go ahead and do this. All right, so now I have written here all the information we need in order for us to find the exact value of the two following expressions. Okay, so same procedure, just like in sine and then cosine. Okay, so first let me write this as angle theta, that what we are solving here. So inverse tangent of -1. Okay, and then I can now rewrite this as tangent theta, which is equal to -1. We know that if the tangent, remember, principal interval would only be from negative pi over 2 and then pi over 2, which again, those are located in quadrant 1 and quadrant 4 only. Okay, so now, since we are looking for the tangent that is a negative sign, so therefore, that must be located in quadrant 4. So you have to remember what we are solving here is located in quadrant 4. And then also recalling the example that we did from sine function or the inverse sine, that when we were working on a measurement that is in quadrant 4, remember that it will not be the counterclockwise, because if we are working on a counterclockwise direction of the angle would be beyond the principal interval. So what we can do here is that we are going to apply the concept of the clockwise direction rotation of the terminal side. So with that, the measurement then would be in the principal interval, which is the negative pi over 2 and pi over 2. And at the same time, that angle will be in quadrant 4. Okay, so now what we are expecting here, since we do have here a negative sign for the tangent that is in quadrant 4, what we are expecting for the angle would be a negative angle, since we are rotating that clockwise to be so that the measurement would be still in the principal interval. Okay, all right, so now moving on to the tangent theta, it is -1. So obviously here, in this case, it's either this two, I mean this triangle right here or this triangle right here, okay? I am not saying that this triangle is applicable to that, okay? I am just maximizing my space here to show you the two special right triangles. Okay, now, we know that that tangent is ratio between sine and then cosine, or for the right triangle, this is opposite over the adjacent. And if we are looking for a value that is equal to a 1, so therefore we need to have value for the opposite and adjacent that are equal. Okay? Again, we need to look for a value for opposite and adjacent to be equal so that we can simplify it into, we'll go down with just +1. So we see here under the pi over 4 triangle, special right triangle, here we have two sides here that are equal, which is the radical 2 and then radical 2. So we can use this triangle in order for us to find the angle theta. Okay, so remember, tangent angle theta is opposite over adjacent. So we can see here radical 2 is opposite to pi over 4, and then of course adjacent to that would be pi over 4 is radical 2, which gives us exactly the same value. So if I'm going to write that, right, okay, let's say we have here, so if we have tangent pi over 4, okay, which is equal to radical 2 over radical 2, we get tangent pi over 4, which is equal to radical 2 over 2 is 1. So we have achieved our goal to have an output which is 1, okay? But remember, like I mentioned earlier, that this pi over 4 needs to be inside this principal interval. At the same time, it needs to be in quadrant 4, okay? And then in this case, we know that pi over 4 is in quadrant 2, so we cannot accept that pi over 4. What we can accept if that pi over 4 would be in quadrant 4. And so in that case, what we can do is to rotate the terminal side clockwise, okay? So in that case, we can rotate that by negative pi over 4, so that we can achieve our sine in quadrant 4 where tangent is negative. Okay, so there you go. We now have here, we can now say that the angle theta is equal to negative pi over 4, or the inverse tangent of negative 1 is equal to negative pi over 4. Okay, so there you go. Okay, so either of these two, how you write your final answer. Okay, that is again the inverse of tangent of negative 1. All right, now moving on to the second statement, which is the inverse of tangent of radical 3 over 2. Okay, so in this case, we have here that radical 3 over 2. Again, we now say that this radical 3 would represent the opposite side, that adjacent side would relate to our adjacent side. So let me go ahead and write this way first, that angle theta is equal to that tangent or inverse tangent of radical 3 over 3. Or we can rewrite this as tangent theta is equal to radical 3 over 3. Remember, like I've said, this is a ratio between sine and then cosine, or opposite over adjacent. Now, I see here that radical 3 over 3, I see that this radical 3 here may be once again included in our um, given expression here. Okay, so what we can do here is to okay, so let me go ahead and circle that value first. So what we can do here is to substitute that value. Okay, so those two given values here. So the question here is that what would be the angle here? Would that be angle pi over 6 or pi over 3? Okay, so in this case, well, you can try it. You can try, but over time, you will actually get used to it. That when you see that radical 3 over 3, you will it would be a second nature to find. I mean, you will automatically see what angle does it represent for the radical 3 over 3. But let me just go ahead and show you why I chose this angle over the other angle. So if I have here, okay, let me just write it, and then I'm gonna go erase it afterwards. If I have tangent pi over 3, this would be again opposite over adjacent. So that would be radical. Opposite is radical. Um, I have radical 3 over adjacent is 1. Versus if we have tangent pi over 6, which is equal to opposite is 1 over adjacent is radical 3. Again, I am just basing on this given triangle here. Okay. All right. So now we have here that if you are going to simplify this, this is just simply radical 3. And that is not what we are looking for, okay? Now, for the second statement, if we're going to simplify this by rationalizing the denominator, we are going to get a radical 3 over the whole number 3. And as you can see here, this is what we are looking for, okay? Which has um, angle, which is pi over 6. So with that, I will now say that tangent pi over 6 is equal to radical 3 over 3. Okay, so you remember that pi over 6 has a radical 3 over 3, but for the pi over 3 has a value that is equal to radical 3 only. All right, so let me erase this. Okay, so now it's time for us to check whether the answer, the pi over 6, is correct. Remember that we are working on the positive output under the tangent. And then we know that if the output is positive, that is located in quadrant 1 or quadrant 3. And obviously here, quadrant 3 here is not included. So we are only in quadrant 1. Okay, so the question here is that is pi over 6 is in quadrant 1? We say yes. Is pi over 6 within the principal interval? We can say yes. So therefore, we can now declare that the angle theta is equal to pi over 6, or the inverse tangent of radical 3 over 3 is equal to pi over 6. So either of these two, how you write your final answer, okay, it's fine. All right, so that is now the inverse, how we find the inverse of the tangent. Just like in sine and cosine, just remember the definition of tangent, their its principal interval, and then which quadrant that interval is located. Okay. Now, one common mistake students make is forgetting the range restriction. Okay, forgetting the range restrictions. For example, if the tangent theta equals to a negative one, then there are we know that there are infinitely many angles that satisfy the equation, right? So, however, the inverse tangent is only allowed to return one angle. Therefore, we always select the angle that lies within the principal interval from negative pi over 2 to pi over 2. Also, you have to ask yourself which quadrant that terminal side is located. So you have to make sure that these two satisfy your final answer. Okay? Remember, is my final answer inside the required interval? And if that is it inside those quadrant, okay, that is in the inverse of that given function, okay? All right, so at this point we have studied the three inverse trigonometric functions that are used most frequently, which are the inverse, inverse sine, inverse cosine, and inverse tangent. But you all know that there are also inverse cotangent, inverse cosecant, and inverse secant function. Although they appear less often in pre-calculus, it's still important to understand how they work and how to evaluate them. Okay, so now let's take a look at the next function. All right. So, like I mentioned, so far we've focused in inverse sine, cosine, and tangent because they are the inverse trigonometric function used most frequently in math, science, and engineering and in calculus. So, however, there are three additional inverse trigonometric functions. Like I mentioned, the inverse cotangent, the inverse cosecant, and then the inverse secant. Okay, so these functions are defined in similar ways. So each restricted domain so that the original function becomes one to one and therefore has an inverse. So while you may not use this function as often as inverse sine, inverse cosine, or inverse tangent, it's still important to understand how to evaluate them and interpret their answers. So the process is exactly the same, like I mentioned, always, like I'm mentioning, ask ourselves what angle produces the trigonometric value. Then we will select the angle that satisfies the appropriate restriction. Okay. All right. Now moving on to the example. All right. So now in here, I have emphasized those restricted intervals here, the principal intervals here. So the principal intervals here for the inverse cotangent, remember, it's from 0 to pi, which is in quadrant 1 and quadrant 2. Now for the inverse cosecant, although it is located in quadrant 1 and quadrant 4, you have to remember also that 0 angle here is not included. Okay, and then for inverse secant, so this is again in quadrant 2 and quadrant 1 and quadrant 2, and also you have to remember that that pi over 2 right here is not included. Okay, so it's a little bit different from the previous inverse function that we had from the sine, cosine, and then tangent. Okay, now looking at that, this example, applying those rules, so cotangent or inverse cotangent theta, you have to remember that the inverse cotangent theta has terminal side located in quadrant 1 and quadrant 2 only, and then the principal interval would be from 0 to pi. So let me go ahead and start writing this as the angle theta, which is equal to the cotangent or inverse cotangent 0 radian. Okay, so I can now rewrite this as cotangent theta, which is equal to 0. And now I am not gonna evaluate this with the cotangent theta only, but I will replace the cotangent in terms of its definition, in terms of sine and then cosine, or the definition under the reciprocal identity. And we know that the identity for the cotangent theta is equal to cosine theta over the sine theta. Okay, so this is now equal to 0. Okay, we know that the denominator of any number would always be equal to 1. So this is 0 over 1. So let me just go ahead and cross multiply this. Okay, so now we get cosine theta, which is equal to, well, sine theta times 0, that would be equal to 0, right? Okay, so now we will now be evaluating that cosine theta, which is equal to 0. Like I mentioned, that cotangent is located in either quadrant 1 and quadrant 2. Okay, now we see that cosine theta here is equal to 0. So we know that where the x value is equal to 0, that would be along with the y-axis over here. Okay, just like what we have from the quadrantal angle. Okay, so let's say this is 0, 1, right? We can clearly see that the cosine theta here is equal to 0, which is the x value here. Okay, I'm sorry, this is an output. I think I had mentioned earlier that this is a radian. No, that is not the angle. Okay, that is the output 0, which is the x coordinate. Okay, so now we have here, since the cosine theta is equal to 0, so that means to say that this angle right here, okay, what angle do we have there? What is the opening of the angle? Rotating that counterclockwise, that would reach that x equals 0. That would be that pi over 2. Okay, that quadrantal angle, that pi over 2. All right, so we see here that the angle theta now would be equal to pi over 2. Okay, okay, because of this concept. Oops. Okay, or you can write this as inverse of cotangent 0 is equal to pi over 2. Okay. All right. So remember to check your answer. Is pi over 2 within the principal interval? We say yes because we know that the principal interval for the inverse cotangent is from 0 to pi. And then also we know that pi over 2 is within that given interval, which is this interval right here. Okay. And pi over 2 is included. All right, now moving on to the inverse cosecant, which is a negative one. So I'll do exactly the same thing. I will not evaluate this with the cosecant. Rather, I will use their identity. Okay, so we have here cosecant angle theta is equal to inverse cosecant of negative 1. So this is now cosecant theta, which is equal to negative 1. All right, now I will apply the identity of cosecant. We know that the cosecant is the reciprocal of sine. So I can also say that this is 1 over sine theta, which is equal to negative 1. And then once again, this is just simply over 1. I can now cross multiply this. So I can now say that this is negative sine theta is equal to 1. Okay, and then I will just move multiplying both sides by negative 1 to completely isolate the sign. So now we have here equal to sine theta is equal to negative 1. Okay, so once again, we see an output which is a negative 1. Now I am seeing a value that would be a quadrantal angle. But you have to recall that cosecant or inverse cosecant has the interval which is from negative pi over 2 to 0 or 0 to pi over 2. But remember, 0 is not included in the interval. Okay, so Yeah, in terms of the graph, these are located in quadrant 1 and quadrant 4. All right. So since we have here a negative sign, let me just go ahead. Okay. So either quadrant 1 or quadrant 4. Okay? Since we're talking about a negative sign here, so definitely what we are looking for would be a terminal side or an angle that is located in quadrant 4. Okay? So that means to say that the angle here that we're looking for would be a negative angle. All right. So in this case, since we do have this a negative one, so where can we find that? Where y, we know that side is y coordinate, where y is negative one. We see that if we're gonna go back with the concept of a quadrantal angle, we see that the y here, which is a 0, negative 1, is the y coordinate, which is the sine, okay, is what we are looking for. And what angle do we have there? If we're going to rotate that clockwise, we see that an angle which is a negative pi over 2. And then negative pi over 2 is still within the range of inverse cosecant. So we can now accept that angle. Okay, so this is sine that negative pi over 2 is equal to negative 1. Okay, so we can also say that angle theta is equal to pi over 2, negative pi over 2, or you can say that inverse cosecant of negative 1 is equal to negative pi over 2. Okay, so that would be now our angle. All right. Okay, so next one is the inverse secant of negative 2. Remember, the inverse secant, okay, is located from 0 to 2 pi. So, sorry, from 0 to pi over 2, which is in quadrant 1, and then from pi over 2 to pi, which is in quadrant 2. What it means there is that the pi over 2 here itself, at that exact location, that is not included in the interval, in the principal interval of the inverse secant function. Okay, so now let's begin. So I can now write this as theta is equal to secant or inverse secant of negative 2. And then this is secant theta is equal to negative 2. Now, converting this into its reciprocal, this is 1 over cosine theta, which is equal to negative 2. Again, I just applied the identity under the reciprocal identity of secant, okay? So now I will do cross multiplication. So multiplying this across. So now we have here that negative 2 cosine theta is equal to 1, wherein cosine theta is equal to negative 1 half. All right. Okay. So now, since I have here a negative 1 half, definitely this is not a quadrantal angle, just like what we have here from the previous two expression. So what we're going to do is to apply the special right triangle, which is the 30 by 60 or the pi over 6 by pi over 3 by pi over 2 special right triangle. And then we have the standard measurement, which is a 2, and then the 1, and then the radical 3. And then since I am working on that 1 over 2, so we are looking at the 1 and then 2. And then again, since I'm working on the cosine, which is an adjacent over hypotenuse, so I'm going to go look for an angle that is adjacent with 1, which is the pi over 3. Okay, so now we have here that cosine pi over 3 is equal to positive 1 half. Okay, I am saying it's positive 1 half. And remember, what we are looking at here, since we have here a negative output, okay, a negative output, that means to say that we are working on quadrant 2, okay, not in quadrant 1. Because remember, as soon as you see here, you might say that, okay, pi over 3, this is my final answer, which is a common mistake. So remember, this is pi over 3, which is equal to positive 1 half. What we want here is the negative 1 half, which is a negative quadrant 2. So what does it mean by pi over 3 here? This pi over 3 is simply the reference angle, okay, that we are using that is equal to 1/2. So if we are to visualize that, that is in quadrant 2, which is in here, which has pi over 3. Okay, what we want is this angle. All right, that angle. So therefore, what we're going to do is to just subtract that pi over 3 from pi. So pi minus pi over 3, which is equal to 2 pi over 3. And this is 2 pi over 3. And that's the angle that we are looking for, so that we will keep that quadrant that we are required. I mean, where the terminal side is located. Okay, so therefore, we have here now that cosine 2 pi over 3 is equal to negative 1/2. Again, that angle theta is equal to 2 pi over 3. You can also write this with the secant or inverse secant of negative 2, which is equal to 2 pi over 3. Okay, so either way, how you write your final answer is fine. Okay. All right. Okay, so once again, at this point, you may be wondering whether you need to memorize all those six inverse trigonometric functions. For this course, the most important inverse functions definitely would be the inverse sine, inverse cosine, and inverse tangent. These are the functions you'll encounter most frequently in the future chapters, especially when solving trigonometric equations and triangles. However, understanding inverse cotangent, cosecant, and secant helps reinforce the overall idea of inverse trigonometric functions and strengthens your understanding of the relationships among the six trigonometric functions, even the concepts that we have learned from the previous section. So the key takeaway here is this: every inverse trigonometric function works by reversing the original trigonometric function and then returning an angle. Okay, so at this point, let's just go ahead and apply our calculator in order for us to find the inverse functions. Okay, so these are, once again, the graphs of the inverse functions, right? Okay. Now let me go ahead with the first one here, which is the inverse of cosine, okay? So whatever your calculator is, I am using the Casio calculator. So all you need to do is, again, of course, you have to make sure that whatever we are looking for here. Let's just say we want to find the angle here in radian. Okay, so for example, we want to look for the angle that is in radian. If you're gonna go back with my video about the use of the calculator, okay, I have shown you where we can find, where we can set up our mode into a radian instead of a degree. Okay, so first thing, again, set your calculator in a radian mode. Second, you have to press shift. Again, I'm using a Casio calculator. You have to press shift in order for you to use the inverse cosine. Okay, so inverse cosine. And then you just need to enter that 1/3 directly on your calculator. So this would be, should be equal to 1.2310 if we are working on, I mean, if we want to finalize our answer with 4 decimal places. Okay, now same thing with the second statement. Okay, you can go ahead and compare your answer and see if we are getting the same result. This is approximately equal to a negative 1.5429. Oops. Okay, hold on. Okay. 1, 4, okay, let me just write in here. So negative 1.5429. Okay. All right, there you go. All right. So once again, at this point, it is important when you it's important, of course, to recognize when an exact answer is possible and when an approximation is necessary. Okay. If the value corresponds to a familiar angle, we should use the exact value. Okay, what do I mean by familiar angle? Like, for example, the pi over 2, which is the 90-degree angle, or the quadrantal angle. Okay, and the angle that is within the special right triangle, like pi over 3, pi over 6, pi over 4, or in degree, 45 degrees, 30 degrees, or the 60 degrees. Okay, so again, however, we should, when the value does not correspond, like I've said, for the special right triangle, if those values are not within those angles that I have mentioned, so a calculator approximation is appropriate. Okay, so in future chapters, especially when solving real world application and triangles, many answer may require calculator approximation. So you need to identify. So if it is possible to express your answer in exact value, you have to write your final answer in exact value. All right. If otherwise, you need to approximate your answer. Okay, now that we have learned, okay, how to evaluate inverse trigonometric function both exactly and approximately, let's explore one of the most important ideas involving inverse function. So recall that inverse function undo each other. So in the next section, we will see how trigonometric functions and inverse trigonometric function interact when they are composed together. Okay, so understanding these inverse properties will become extremely important in chapter 5 when we begin working on trigonometric identities and equations. All right. Okay, so before we begin with the example, as you can see, we do have here the inverse properties. Let's take a moment to think about what inverse functions actually do. Okay, recall the inverse function undo one another. Think about multiplication and division. If you multiply 5 divided by 5, you end up right back where you started, right? Um, Again, the same idea applies to a function and its inverse. So if the function followed by its inverse, the two operations cancel each other out. Okay, so for example, if we take the inverse of cosine of a number, then immediately take the cosine that result, we'll get to back to the original value. All right. Okay, so let's go ahead. So again, this inverse property only work when the inputs and outputs stay within the restricted domains and range. Okay, so that is why this is why understanding principal values is so important. So let's see how these properties work with the practice part here. I'm in the example. Okay, let's take a look at the cosine and inverse of 0.7. Okay, so we can say here by inverse properties. Okay, let me just go. All right, by inverse property of cosine of inverse cosine of x equals x for x is has a range from -1 to 1. Okay. Now, what I just meant here is that I'm writing it in a formal way. I am using the inverse property, which is the cosine of inverse cosine of x equals x for all values of x, which is from -1 to 1. And then, as we can see here, that the value for x here is zero point 0.7, which is within this range. Then I can now apply this property. Then I can now say that cosine of inverse cosine of 0 0.7 is equal to 0 0.7 as well. Okay, there you go. All right, next part, we'll have here the inverse of sine theta, okay? Also, I can still see some inverse property here. So by inverse property, what I see here is what I can apply here. Now I see the inverse sine of sine x, which is equal to x. When the value for x is from negative pi over 2 to pi over 2. Okay, then now I can now say that that inverse of sine theta, okay, which is in this case I have here that sine theta right here is simply sine, oops, that's sine inverse, which is equal to 0. Okay, now we have here that sine inverse of 0. Okay. Now you go back with our lessons when we are looking for that inverse of sine. Okay. So we know that the output of sine, which is 0, then this would be equal to 0. Okay. Because remember, this is from quadrant 1 and quadrant 4. Okay. So therefore, the angle here would be a 0 for the inverse of sine. Again, what I have applied here from this second part of the statement are the concepts from the previous example for the inverse sine. Now, how come I did not use this inverse property? Okay, so that inverse sine of sine x is just equal to x. Okay, how come I did not conclude here that this would be equal to pi? It is because, okay, although it is written with the same way in the first statement, it is because the range of pi, okay, of the given here is beyond the range of the given property. Okay, so it does not cover this property for us to say that this given statement is just simply equal to whatever input here, which is the pi. All right, so if that's the case, then what you can do is you will apply what we have learned from the previous concept. Okay, all right. Okay, so next one. So I think, okay, so let me just complete my statement here. Okay. Okay, so next one we'll have here that cosine of inverse cosine, which is negative 1.2. Okay, so now we will be writing this as by inverse property. Okay, cosine of inverse cosine of negative 1.2 is equal to x, for x is from negative 1 to 1. Okay, then, okay, you can now identify whether this property is applicable or not. Yeah. Okay, so we have here cosine, inverse cosine of negative 1.2 is again not equal to negative 1.2. Okay. Actually, the answer here would be undefined. Okay, let me explain that why. All right. So first thing, we cannot say that this given expression right here can be applicable for this property. Why? Because as you can see here, this output right here, negative 1.2, is beyond this given input, which is a negative 1 to 1. And then also, you remember that an output for the cosine, if it is more than for the cosine, if it is more than 1, remember the range is only from negative 1 to 1. If it is beyond those values, that means to say it does not exist, because remember, cosine only oscillates from negative 1 to 1, from negative 1 to 1. So that means to say this output negative 1.2 is not even existing in the given range. So therefore, our answer here, since this value right here, this part right here does not exist anymore, so the entire expression we can now say it does not exist, which is an undefined. All right? All right. So once again, okay, I think this is the last examples that I have here. So again, these examples highlight two important ideas. First a trigonometric function and its inverse can often cancel each other. Second, those cancellation will only work when the values satisfy the required domain and range restrictions. So as we move into chapter 5, you will see those inverse properties appear frequently when solving trigonometric equation and simplifying expression. The more comfortable you become with these restrictions now, the easier those future topics will be. All right. Okay. So once again, I think let me just see the next page. All right. All right, there you go. So, congratulations. So, you have now completed chapter 4. So, let's take a moment to appreciate how much ground we've covered. So, we began the chapter by introducing the sixth trigonometric function using the unit circle. And then we learned how to evaluate the exact values using the reference angles and determine the signs of trigonometric functions. And then we explored the graphs of sine, cosine, tangent, cotangent, secant, and cosecant function, including their transformation. And also, we have introduced fundamental trigonometric identities and used them to evaluate and simplify trigonometric expressions. And then finally, in today's lesson, we have learned how to work backward using inverse trigonometric function to determine angles from trigonometric values. All right, so everything you have learned in chapter 4 provides the foundation for the rest of the course. All right. So, like I've said in chapter 5, we will begin analytic trigonometry where we will study identities, equations, and more advanced relationships among trigonometric functions. Then in chapter 6, we will apply trigonometry to solving triangles using the law of sines and law of cosines. Again, inverse trigonometric function will play a major role in both chapters because they allow us to determine unknown angles. So even though chapter 4 is ending, the ideas here from chapter will continue appear throughout the remainder of the course. Okay, so before moving on to chapter 5, I encourage you um, to complete the checkpoint problems independently. The checkpoint is your opportunity to verify that you understand the major ideas from today's lesson. As you work through the problem, please focus on evaluating inverse trigonometric functions, using the inverse properties correctly, identifying the principal values, and then using the right triangles to rewrite inverse trigonometric expression. Remember, like I'm always saying, watching example is helpful, but real learning occurs when you actively practice the concept yourself. Take your time, show all your work, and make sure you understand why each step works. If you encounter difficulty, review the related examples from before moving on. Once you feel comfortable with this concept, you'll be ready to begin chapter 5, which is the analytic trigonometry. Okay, thank you for watching, and I'll see you in the next chapter.